Hey guys, this video is going to walk you through the 11.2 examples. Make sure that you use your book to also fill in the vocabulary. I'm going to briefly discuss some of these because they do go with the examples. So with this first part, we're talking about different kinds of arcs. So we've already discovered that an arc is a portion of a circle, and its endpoints have to be on the circle. So a minor arc is an arc that is less than 180 degrees or less than half the circle. So we can see over here AC is a minor arc because it is less than half the circle. So if I knew what x was, x would have to be less than 180 degrees. So the notation here is we use the endpoints A and C, and then we use an arc symbol. So kind of a partial circle that overlaps. And so this is a minor arc because it is less than half the circle. So minor arcs, we usually use two letters. I know there are two possible ways to think about AC. It could be this big arc or this small arc. So we usually just use two letters if it's a minor arc. For major arcs, which is this next one, we use three letters to show that it's going the long way around. So a major arc, as you can probably guess, is an arc that's bigger than half the circle, or the angle is larger than 180 degrees. So in this case, the notation would be arc ADC. So we use three letters to show it's going to be this way around versus the short arc right here. So arc ADC, three letters with an arc symbol over it. And this is a major arc. And then this hopefully is not a new term, but semicircle is a half circle. So we have this guy, we can say, again, we'll typically use three letters, but this one we could also use two because EG this way and this way would both give me a semicircle. So it's the endpoints of an arc that lie on the diameter of the circle. So this is a diameter. The arc that goes with the diameter is the semicircle. So again, we could notate this way, or we could say E, F, G, and those would both indicate the semicircle arc. Okay, so 11.2.2. So you want to make sure you write down the theorem. I would say there's three cases, so you can write down the cases here, what's going on. And then these examples kind of go with the cases. So basically in a circle, if I have congruent central angles, so central angles, remember the angles that the vertex lies on the center of the circle. So if those are congruent, then the chords that go with those angles are congruent. So remember, a chord is just a segment that has endpoints on the circle. So this is a chord and this is a chord. So in this case, ED would be congruent to CB. And it works the opposite way as well. Well, I guess we'll start with that first. So if the chords are congruent, then the arcs are also. So whatever this segment is, it's congruent to this segment. If that is true, the arc measures and the arc lengths are also congruent. So their angle measures are the same as well as their length. And then over here, it's kind of the opposite effect. If I know the arc measures are equal, then we can assume that the central angles are congruent as well. Because remember, the arc measure is kind of associated with that central angle anyways. So hopefully this is kind of intuitive for you guys, but we're going to use this idea to help us out. Okay, so we're going to find each measure using this picture. So the first one is JKL. So this is going to be a major arc because they are using three letters, or it could be a semicircle as well. So I'm going to go from J to K to L. Okay, and they're probably doing this as well, just so I know not to go this way or to stop at K, but I know I'm going J to K to L. So three letters can make it more clear too when there's a lot of letters going on in our picture. So measure JKL. Well, from J to M, that's a diameter. So J to M going this route would be 180 degrees because a semicircle is half of 360. So notation here, measure J, K, M, so I'm going from J to K to M all the way, is going to be a semicircle. So the measure of that arc is 180 degrees. Remember, arc measure is an angle. So if that's 180 degrees and this piece right here is 40, if I want JKL, I can just do 180 and subtract off that 40-degree piece. So if I do 180 minus 40, I get 140, and that would be the measure of arc JKL. Okay, now into B, LJN. So L to J to N. So again, we know not to go this way because of the order it's giving me. L, then J, then N. So saying about this major arc right here. Okay, so with this one, we know that a whole circle is 360. That is pretty close to a whole circle. It's just not including these two pieces. So if I do 360 and subtract off this 40 and this 25-degree angle, that would give me what I'm looking for. So I'm going to do exactly that. 360 minus 40 and 25. So 360 minus 65 is going to give me the measure of arc LJN, and that's going to be 295 degrees. Okay, next theorem, 1123. Again, please write the formal theorem down in this box, and this is going to be an application of it. So what this one is saying is that if a radius is perpendicular to a chord, remember a chord is just a segment where I have two endpoints on a circle. If it is perpendicular to a chord, remember perpendicular means it's forming a 90-degree angle, then it bisects the chord and its intercepted arc. So remember, bisect means to cut in two equal halves. So the chord is being bisected. So CD in this picture bisects the segment EF, and also the theorem says it bisects the arc. So that arc EF, and I'm going to say EDF to clarify it's this side of it, and it's an arc. So it's bisecting both of those things. Okay, so I guess we're not really doing an example here, just knowing that those are congruent, and also the arc measures are congruent. Okay, in this one we do have an example. So 11.2-4 theorem, please again write the theorem here. So if a perpendicular bisector of a chord is a radius, the perpendicular bisector of a chord is always going to be a radius or diameter. So if we see it's bisecting and it's perpendicular, this line has to be a diameter or radius if it doesn't go all the way through. So it's kind of the reverse of this theorem that we just looked at. So we're going to use that to find NP. So NP is this chord right here. So we want to find the whole length. I know, we should say in particular, this is a perpendicular bisector. So this is a radius, okay, and a radius bisects a chord if they're perpendicular. It's one of these theorems here. So the radius is the distance from R to M, and remember, radius can be drawn in lots of places. So the distance from R to M is actually 17, right? 8 plus 9. So if I were to draw in another radius, this is also 17. Any distance from the center to the edge of the circle is 17. So if I could figure out this piece, I would just double it to get the whole chord NP. So I have a mini right triangle here, so I'm going to pull that out. Okay, so I want to find this. I know that's 17 because that's the radius. And we know that's 8, that's part of our given. So I could use Pythagorean theorem. I know that's also 90 degrees by vertical angles. Pythagorean theorem to find this x value. So I can do x squared plus 8 squared equals 17 squared. So I've got x squared plus 64 equals 289. Oh, 289. And then I can subtract 64 from both sides, and once I do that, I get x squared equals 225, and the square root of 225 is 15. So if x equals 15, then NP is x plus x, or 2x. So NP is 2 of those 15s, which would make it 30. You do have a problem or two like this in your homework, so the biggest thing is remembering you can draw in a radius and all radii are equal within the same circle. So notice what one radii is, and then no matter where you draw your other ones, they also have that same length.